Dear all, am I audible to you all?
Audible, sir.
Yeah, okay, great. Okay, someone more is there. Yeah, great. Okay, guys, so it's already 3 p.m., so we can start our today's discussion. So, right now we are in the week 3 of the Technique of Material Characterization course. Let's have a look on what are the content that has been covered. So, in this particular week, on the larger scale, 3 lectures we spend on the basics component of the microscopy, and then we talk about the electron material interaction. This entire week was not specifically for any particular technique, for example, SEM or for TM. No, it was very generalized. So how like electron gun is there. So in SEM and in TM, same gun we are going to use, same electron gun we are going to use, just that the energy will differ. Few component will be added. That's already there. And electron material interaction. Try to go with the like surface topology. We can see the SEM low structure now. So before I start with the discussion from my end, let me ask you that do you have any doubt in the content, in the material that has been discussed in this particular week or previous week? You can always respond in the chat box. And if you have any doubt, you can always unmute yourself and interact with me. Great. Since there is no doubt, let let's discuss few concepts, and then after that, based on those concepts, we'll discuss few questions. So see, in the first class, in the first lecture, we have learned that an atom having the different energy states, the electron will be situated in this energy state. So when we are talking about the electron gun, let's say, what is the purpose of the electron gun? It is to get a electron. Like for example, in optical microscope, we are using the light. So we are getting the light from some tungsten filament or some halogen bulb. Here, the source is electron. Like the thing is in electron. So for that, we have the electron gun. To get the electron, we have the electron gun. So now how the electron gun is working? It's basically due to the thermionic emission. So if we take a material, if you heat it above a particular temperature, if the certain amount of energy has been provided to it, so this electron, the outer shell electron, can be ejected from the atom, from the nucleus binding. Okay. The reason is that the outer shell electron is not as stable as the inner shell electron. We can see it's minus 20 keV. And outer shell we are considered to be the zero. This is our assumption that okay, one can anyway consider the potential at any point to be the zero. It's their choice. If we consider this to be the zero, then we'll consider this to be the okay 20 keV. So since it is very easy to eject the electron from here, so we are able to see with the help of the thermionic gun, once we are heating it up, once we are providing sufficient of field, the electron will be ejected from it. So this is the purpose what electron gun is serving. This is the mechanism behind it. Let's see the electron gun. The general structure of the electron gun is something like this. Here we have the cathode, we have the anode, we have the walnut electrode. Let's understand the function of each of them. This filament, let's say right now we can say that it is a tungsten filament. We are talking about the WSU, tungsten filament. Filament can be lab 6 tungsten or it can be single crystal tungsten also. So this one, we will apply some bias across it, okay? So across the cathode and across the anode, we'll apply some bias. We want this cathode, which is tungsten, we want the electron to eject from it. So what is the condition? We just talk that we can do it by applying the heat. One can also do by applying the feed. Okay. So let's say we are doing it by applying the heat. We gave a certain amount of heat to the specimen, to this filament. Now it's ejecting the electron. Now that electron need to be the accelerated. Okay. Electron having the negative charge, it will move. If we want to accelerate it, the anode should be the positive, right? They should attract each other. So the cathode will be at the negative. Clear? Now walnut electrode will also be negatively charged, negatively biased. It will be more negative compared to the cathode. So now what is happening? See, overall picture is that from here the electron is coming, it will traveling toward the anode through this walnut electrode. This bias, we already understand what is the purpose. It is just to accelerate the electron to make it that okay, sufficient energy it should have before it collide with our specimen, so that we can get the interaction, which we are going to talk later on. Now this walnut electrode, now you can see that the electron is having the negative charge. Why we are providing the negative bias to it? There is a purpose for this. The purpose is that here the negative charge, they will repel this electron. Since they will repel this electron, so instead of the diameter, if I see from the top, instead of diameter being this big, it will become smaller. They will repel it, they will try to compress it, right? So the overall cross section will decrease, which is beneficial for our SEM, right? We want to, for any electron microscopy, we want the probe size to be as small as possible. So this was the entire function of the electron gun. Now we are passing some current. Okay, to do that, we are passing some current through the filament. So now we got some intensity, little bit of intensity we have got. We are applying, this is the filament current. Filament current, like we are passing the current through the filament so that it should get heated up. Beam current is the current this is the current, the electron which we are ejecting from this particular filament. This is the beam current. So we are passing some current through this, and we are getting some current over here. Initially, the thermionic emission will not be that sufficient enough, like below this value. It will not be sufficient enough. So majority it will be very dark, like you will not get any electron. So if you are trying to image you put your specimen in the SEM or some electron microscopy, the filament current is somewhere over here. You are seeing everything is dark, nothing is there, right? So now what you will do, you will increase the filament current further, and you can go to somewhere in between this values. So now the electron will start to eject from the filament, and so on and so forth. We'll be able to see the microstructure of the specimen. Whatever the feature you want to see, that will be visible. After certain threshold value, it will be saturated, right? The now electrons are ejected to a very large extent. Even if you increase the filament current further, it's not going to add anything. So this was the entire function of this electron gun. Okay. Now let's try to solve your questions. Do you guys have any doubt in this discussion which we just made? Okay, great. Since now, let's move to question number 1. So true and false. If we don't put anode, what will be the intensity? If you are not putting the anode, let's say that you are not accelerating the electron itself. If you are not accelerating the electron will not reach the specimen. Zero intensity. You won't get any intensity. Okay. If you provide threshold value, you will be able to eject this particular electron. But the entire SEM, the entire operator sitting onto that SEM machine, who is operating that, his function is entirely to make the beam, the optics of the electron, in a, in a, he will adjust that thing so that we are able to get some interaction of the electron with the specimen. So the entire study of the SEM is about the beam optics. What parameter you are going to change? One of the parameter we just saw that. What parameter you are going to change? That is going to affect the beam. Now, if you increase this, you will get some electron. Now, if you are not applying any bias, this electron is of no use then. Like they will not be accelerated. The path will not be provided to them. Right? So you are not going to get any intensity. That was a very good question. Okay. As compared to the bulb, what is the temperature difference in the tungsten filament? As compared to the bulb, what is the temperature difference in the tungsten filament? See, the temperature which we are working on, the tungsten filament which is right now, it is something around 2500 degrees Celsius. Normal light bulb. Normal light bulb is also more or less they work on the same temperature. Okay, the one which we are emitting. You are talking. I think you are talking about that the bulb which emit the orange color, orange light, right? Not this LED bulb. Those things. So the tungsten, yeah, that's it. So more or less they work at the same temperature. Okay, let's go ahead. Let's talk about the first question. When false, outer shell electron in atoms are delocalized and participate in the bonding. What do you think? Is it true or false? Outer shell electron, like we talk about now, there is a pi bond is there, sigma bond is there, ionic bond is there. Is it the bonding is between the inner shell electron or it's between the outer shell electron? The statement has been made in the class by the professor. That's why we are asking this question. The bonding, whether it happened between the outer shell electron or it is happening inner shell electron. In the bonding, will this electron from the inner shell will bond with the inner shell electron of the another atom, or it will be the outer shell one which we will lose, the electron will lose, and it will form the bond. So it's very clear from the class 10+2 we have learned that the one, see for example lithium is having one additional electron in the outer shell. If it lose that, it will become stable. It will become the helium configuration, right? So it's always the outer shell electron is the one, and you can understand that the outer shell electron are the more easy to, they are at the more higher energy state, right, compared to the inner one. The inner one are more stable, negative. Outer one are the one which is comparatively more higher energy state. So stabilizing them is the necessary part. So the one which is at the high energy state, they are the one who is going to form the bond. By forming the bond, they will lose that energy. Okay. So the outer shell electron in atoms are delocalized and participate in the bonding. The answer is true. Okay. Okay. Now let's talk about this. The conduction band and the valence band overlap in the insulator. It's very general questions. Right now we are talking about the. Very good. It's a false, right? The insulator, they are separated. The band gap between them is more than 3 electron volt. Okay, and it's in the metals which we can say that okay, conduction band and the valence band are overlapping with each other. Now in TM, okay, third one, in TM the specimen must be opaque to electron. Should it be opaque or should it be transparent? What do you think? Is it the true or false? In TM, transmission electron microscopy, the specimen should be the opaque to the electron. In TM, we know that we have the specimen. We are passing the electron through it. On the electron will penetrate, it will interact with the specimen, and we will get the information like this. The thickness is too much. If it is opaque, then this we will not get these signals. What we will get the backscattered signals. Those signals we will get. Yeah, that's right. Very good. It's again the false. In TEM, for TEM we need the transparent specimen. Last one. The secondary electron in the SEM are emitted from the deeper region of the specimen than the backscatter electron. Now this question has been, we have saw the electron material interaction. So in the electron material interaction, what we know that secondary electrons are emitted near to the surface compared to the backscatter electron. So in the secondary electron SEM, secondary electron in SEM are emitted from the deeper region. The answer is no. Compared to the backscatter, it's the other way around. Secondary electrons are the one which is having less energy compared to the backscatter electrons. Energy of secondary electron is less compared to the energy of backscatter electron. Since the energy is less, it cannot be ejected, it cannot be removed from the what we can say deeper region of the specimen. It will remove only from the near region because it will need some energy to come out of the specimen, right? So that's the BSC having a large energy, it can eject from the deeper region also, but SC since it's having the lower energy, this is how it is. Okay, so till now, any doubt in this particular, the question number 1? Answer is false. Any doubt in this question number 1? If yes, please let me know. If not, let's move to the question number 1. Yeah, please let me know. You can always unmute yourself and interact.
Sir, am I audible?
Yeah, you are audible. Please go ahead.
Okay. So as you said that in the previous image you showed, like the different shells were there, KLM, and in that the outer shell was having the more energy than the inner shell.
Yep.
So outer shell will have more energy, which can be easily removed.
Yeah,
May I
definitely.
know?
Mhm.
Yeah. May I know in the same? Can you connect this with the SCM? The last option which you said.
Okay. See, the way the signals are generating in SEM, SE signals. In SEM, two signals we talk about SE, and another one we are talking about the BSE. The SE signal is the one. Okay. The SE signal is inelastic. Is coming due to inelastic scattering. BSC is coming due to the elastic. Now, in inelastic, what is happening? See what is happening. The beam which we just talked, like we have generated the beam. We have generated this beam. This beam is going to interact with my specimen. Now it can generate two things. It can interact with the specimen in inelastic way. It can interact with the elastic. Let's say this electron is there in the specimen. My incoming beam came. It interacted with it. Due to its high energy, the incoming beam is having the high energy. What it will do, it will knock it out. Now it will knock it out and it will remove and it will be counted as the SE signal. Now one more thing can happen. Now my electron, the incoming electron is going like this. Now this electron is in the effect of the nucleus. Nucleus is having the positive charge. Electron is having the negative charge. We know when this thing happen that what can happen, the path of this particular negative charge, it will try to deviate. So what can happen? It can go like this. It's just like the electron are revolving around the nucleus. This will also be thrown back by the force. Okay, the force of attraction. So it so now what is happening on an average here? The one which we are getting here in the BSC mode, this electron was the one which was initially we passed through the specimen, right? So this one is more or less having the energy of the primary electron. This one, the SE one, is having the lesser energy, right? Since SE is having the lower energy, it will be difficult. See, let's say this electron is there at the quite depth, and this electron is there somewhere near to the surface. What do you think? They both are having, let's say, the same energy. E1, E2, they are both are same. Which one is easy to remove, E1 or E2? It will be easy to remove E1, right? Because it cannot. The electron, yep, very good. It's E1. E1 is easy to remove, even though they have the same mass. Now you think, if I'm keep on increasing the energy, it is very easy for the electron to come out of the specimen. So that's the reason why the BSC signal can be generated even to a lower depth, like even deeper compared to the SC signal. It is happening due to the energy. It is happening because the way they are interacting. SC is interacting with the electron. In SE, the primary electron is interacting with the electron of the atom, while in BSC, the incoming electron is interacting with the nucleus of the atom, nucleus of the specimen, right? So this is the overall picture. Let me know if it is clear. If not, we can have a... Okay, it's clear. Great, guys. Let's move ahead. Let's go to the next question, question number 2. So now in the assignment, you will find one question, something like this. Again, the values are changed, but concept will remain same. Now an electron is accelerated through a potential of this. We talked here, right? That we are accelerating the electron by the application of the field, by the application of the voltage. So now how much the voltage applied? 200 kV. Ignore the relativistic effect. Let's ignore this. Like, we know that when we are talking about the charged particle, the effect of the mass will also be, like, since the mass keep on changing with respect to the speed, we have to take it into account. Question has made this thing clear for us, that okay, easy for us, that okay, let's ignore that part, don't worry about that. Now let me know that what is the right answer. Okay, we have to calculate the de Broglie wavelength, right? So we know the de Broglie wavelength is given by h over p. So what we can see, we also know that energy is equal to the half mv square. So you might have known some formula to solve this equation. I don't remember those formulas, so it's very easy since we can derive it easily. So now I can multiply the mass on both the side, me, what I will get, half m square v square. M into v, we know that it's nothing but a momentum, right? E here is the energy, right? So now let's put it. We know the h divided by root over, sorry, p will be 2 me. E is the energy. We know if this much amount of potential has been applied for the charged particle q, let's say E, so it will gain the energy of E into V, whatever the voltage that has been applied. So let's write that thing. We know that energy can be written as E multiplied by this voltage V. So this is the formula which is beneficial for us. It will be given as h divided by root over 2 me V. We know all the things. We know h, we know m, we know E. The V is given to us 200 kV. So we'll put it as 200 multiplied by 10 to the power of 3. You will get the, since we are putting all the values in the SI unit, what we will get? We will get the wavelength in the meter. One can always convert it to the nanometer. Okay, so let's try to do it. Let's try to find its exact value. This is the formula which we are going to use. I will put the value of H. H is root over 2 ME. Then I have to put the charge also. Then I have to put the this voltage, that is 200 multiplied by 10 to the power of 3. So what I have got is, the value which we have got is around 2.74 into 10 to the power of minus of 12 meter, right? So we can write it is nothing but 2.74 picometer. So this is our answer. Let me know if anyone find any difficulty in this entire process that we have carried out. If not, let's move ahead. So you will find one assignment question of similar type. You can solve it in the same process, or you can directly use this particular formula. All we have to do, we just have to put the values. Make sure that you put all the values in the SI unit. If one unit is not in the SI unit, then again you have to do the conversion. So with that, we have solved the question number 2. Let's move ahead to the question number 3. So we discussed about the function of the walnut cap. What it was. We are talking about this thing, this walnut cap. What is the primary function of the walnut cap in the thermionic emission gun? What do you think? To accelerate the electron toward the anode? To repel the electron and create a crossover point? Very good. So Ritu has answered that. It's the option B. To increase the temperature of the filament? No. This is not the function of the walnut cap. To measure the beam current? No. To accelerate the electron toward the anode? That is a part of the bias which we provided across the anode and cathode. It's not the function of the walnut cap. Very good, guys. So instead of this much size, like we can decrease the size of the crossover by the use of this walnut cap. Okay, any doubt, let me know. If not, let's move ahead to the next question, question number 4. All these are very easy, we have already discussed. So now, the I dark current is in a thermionic gun referred to A, B, C or D, which one it is. So right now we are talking about this dark intensity, right? So now under what condition it will come? Maximum beam current, filament current before electron emission begin, current due to the secondary electron, residual gas ionization current. What is the right answer? So very good, it's a B. This is the point where thermionic emission begin. Before that, there will be very less or no thermionic emission. Okay, so it's the option B is the correct answer. So you will get that dark, like it will be very less. You won't be able to image your specimen. You won't be able to see the microstructure. Okay, very good. Let's move ahead. Let's go to the question number 5. Now the brightness. For the brightness, we have discussed one formula. I have noted it down. Yeah. So brightness is given as 2 into 10 to the power of 5. See, values doesn't matter to us. 2 into 10 to the power of 5, those things doesn't matter. What matter is on what parameter is going to depend upon. This is the work person. So the brightness, let's see. V is a voltage. Okay, V is a voltage, T is a temperature. V is the voltage, the bias which we provide across the anode and cathode. This phi is a work function. We know if one work function is higher, it will be very difficult for us to remove the electron from the specimen. If the work function is low, we can easily eject the electron from the specimen, right? So phi, lower phi, it means that easy to eject the electron, more electron you will get. It means that the more electron concentration will be more, the beam current will be more. Beam current will be more, so we know that the brightness will be more. Right? If the temperature is more temperature, more we are hitting that gun to a large extent. More the temperature, more electron will eject, more electron, large beam current, brightness again will be more. The voltage, see, we don't vary the voltage for the brightness. More or less we try to keep it same. For example, there are the TM who are specifically designed to work 2200 kV, 300 kV, like that. But still we can understand that if we increase the voltage, we are increasing the, what we can say, we are increasing the energy. More is the energy with which it is tracking the specimen, the brightness again will be higher. Okay. So now based on the discussion which we have made on the brightness part, can we answer this question? The brightness decrease exponentially with temperature, is independent of the work function, increase with both temperature and the work function, is maximized by high temperature and low phi. What do you think? Brightness, for more brightness, we need less work function. Very good. The right answer is option D. Higher the temperature, lower is the work function, electron get emitted. We have a question. So we have a question. The electron get emitted due to the thermal energy given to them. If the anode is not there, what kind of trajectory do they follow? It will be very random. They won't follow any trajectory. It's like you can think of it like you turned on the bulb, it's emitting the light in all the directions. So this is what is going to happen. If just thermionic emission is there, it will eject depending upon the shape. If your shape of the gun is like this, if the shape of the gun is like this, it will just follow some random trajectory. It will not. What is the sink of those emitted electron? We are already providing the bias to them. Okay, the bias is already provided. So with the help of the detector, we are able to see what is going on. So the ground is already provided to them. If not provided, it will create the charging in the specimen, which is not good. Right. Okay, these things again we will discuss when we will discuss in detail about the SEM. There will be a concept of charging will come. We'll see those things also. Okay. Yeah. So till now it is clear. Is the question number 5? If any doubt, let me know. If not, let's move to the next question. Question number 6. The path of the electron through an electromagnetic lens is, among this, what it is. See what is happening. Let me keep that particular figure ahead. Yeah. We have the electron source. We have an anode. We have a condenser lens. More or less, we have the lens. Electromagnetic lens we can call. Condenser lens, objective lens, those things we are having. Again, we will discuss in detail about these lenses. So what is happening in the lens? How the lens is this particular lens is working. We are providing the electromagnetic that magnetic field is present in them, right? So our electron is not going in the straight path, which we usually draw with the straight line. Okay, this is trajectory, this is the optical path. Instead of that, it go in the helical path. It's rotating. The electron is also rotating due to the application of the field, magnetic field. We know, let's say, if we have charge q, it's a magnetic field, and due to some voltage, like, sorry, it is a velocity of the electron, velocity of the charge particle. If a charge particle moving with a velocity v, in the effect of magnetic field B, it will experience some force, right? This is going to provide the magnetic field. Velocity, we have already gathered some velocity just by accelerating them from cathode to the anode. Velocity we have. So now it's moving downward. It's also due to the magnetic field. We know magnetic field is used to change the direction. So it will change the direction. So not only the downward movement, it will also show some spherical movement. These things we have discussed. Okay, so V cross B. If it is electron, you can just replace them. Like in our class, what professor has wrote is B cross V times charge. He already considered that, okay, electron is having the negative charge, so we can interchange them. So so the only thing that we need to keep in mind from this discussion is that the electrons in the SEMs, they are not following the straight path, they are following the helical path. Okay, so based on this discussion, we will be able to answer this. What is the path of the electron through an electromagnetic lens? A, B, C, or D? Random is the one which we talk, okay, no anode, we are not applying any bias. So we know that this is not going to happen. A straight line, we decided that it's not going to happen. Parabolic path is not there. The only thing is right, it's a helical path. Very good. So Ahmed had told that the option C is the right answer. Very right. Okay. If any doubt, guys, let me know. If not, let's move ahead to the next question, question number 7. Guys, everyone try to answer this question. It's very easy. What component creates the magnetic field in the electromagnetic lens? You know, in the transformer, we use what we are using to create the magnetic field in that. The function of the tungsten filament is to generate the electron. It's not to create the magnetic field. Glass envelope, no, it's not there. Aluminum pole, no. We are using the iron pole, first of all, not aluminum pole. So, even in the fan, you can see, in the transformer, we can see that it's a copper coil. The current passing to the copper coil will create the magnetic field, right? And this is the component of what we are using in the electromagnetic lens. The entire electromagnetic lens is comprises of the copper coil. We have set of copper coil, and a current is passing through them around 0 to 1 ampere. And with that, we are able to generate this electromagnetic field. Okay, very good. Yeah, so option B is the right answer. Okay, few more couple of questions. Let's discuss on this particular theme. What problem does the helical path of the electron cause in imaging? Image distortion, image rotation, color aberration, loss of resolution. If the electron, the path, if it is rotating, if it is it's in the helical path, so what will be the problem in that? The problem which it will create, it will be the image will be rotated by a certain angle. If the number of path is not integer, the number of path is not. If it is an integer, you won't face any rotation in this. But if it is not, the number of circle is not, if the number of rotation is not integer, then in that case you will face the image will be rotated. So you might have created your specimen like this, but you will see, okay, to by certain angle it is rotated. So this is the question number 8. If any doubt, let me know. So now, yeah, one more thing. Question number 9. Yeah. See, we are keep talking little bit. We are trying to get more information. I am trying to add a few things more. Even though we are not completely discussing about what is the path of the secondary electron emitted. Path of the secondary electron. Helical. It's a good question. Let me think. Objective lens is there, it's passing through this, specimen is there, okay. But it's not under the effect of the magnetic field. So it won't be helical. It won't be helical because it's not in the effect of the magnetic field anymore here. Right. So it will be like, since that whatever the beam, wherever the region, from that particular region you will get the information. So it just from wherever it is emitted, it will follow the same trajectory, right? So it's like if it is emitted from the feature which is like this, so it will follow the same trajectory. It's just like that the detector will apply some force which will attract these electrons. So the way they are emitted, it will be as it is reflected onto the detector and we will be able to see. That's a good question, but I will think more on that. Yeah, so I was going to say why magnetic field will not apply. Because condenser lens is here, objective lens is here. We are keeping the secondary electron detector in between them. Okay. So it's not the specimen, from the specimen we are getting the electrons, right? Those electrons are not under the effect of the magnetic field from these two things. Our detector is somewhere in between the objective lens and the specimen. That's the reason why it will not be under the effect of the electric field. It will not be under the effect of the magnetic field. Okay. Very good, Prahlad. So this was the reason, and yeah, so I was going to say something regarding the scanning electron. Scanning coil. What's the purpose of the scanning coil? Scanning coil, as we know, the word itself is like scanning. So it will help, this one will help, okay, the electron is going in some particular path. So what it can do, let's say you don't want to examine this particular region of the specimen. You want to examine this particular region of the specimen. So what it will do, instead of here, it will bend the electron beam to this region. So the scanning coil, the entire purpose is to give the trajectory to a particular region, which region you want to focus, which region you want to see the image. So the entire bending path is governed by the scanning coil. Okay. So here it is. Scanning coil are primarily used for what? What do you think? Among all these 4 reasons, among that, which one is the right one? Focus the electron beam, deflect the electron beam, generate the electrons, detect X-ray. Very good. It's to deflect the electron beam. By deflecting the electron beam, we can go to particular region. Okay. How do they deflect? It is again under the effect of magnet. What kind of force? It will be like the magnetic field is applied. So see, we know that a charge can be deflected under the effect of field. Okay, so it is under the effect of electromagnetic field. Again, the coils are same, more or less. The coils, the lens the magnetic field which we are using for the condenser lens and the one which we are using for the scanning coil are more or less same. It's just that this deflection will not rotate the image. This will also rotate the image. Their primary function will remain same. See, the condenser lens and the scanning coil, they are same, exactly same. It's just that they are operating at the different current passing through them. Their force exerted will be different. So we know that we can deflect, we can change the path of the beam, path of electron by applying the magnetic field to it. Okay. So under the applied, right? But the magnetic field is not applied, right? Magnetic field is applied, right? We are talking about this B. Scanning coil. The scanning coil is the same design as the condenser lens. The lenses which we talked just now. Okay. It's just that they are operating at different magnetic field. The strength will be different. And we know under the effect of field, they will get some force, and that force we can manipulate. This is in our hand. B is in our hand. By passing how much current, we can deflect it. We can change its path. Okay. So, and this all the lenses will introduce rotation in the image at the end. Yeah. So this is how it will deflect. Just by manipulating this, manipulating B, it can be manipulated by how much current we are passing through it, and now that will affect this. In return, it will affect this. With the help of the force, we can deflect it. Okay. Let's move ahead. Yeah. Next question, question number 10. Yep. So now, by the way, any doubt till now, please let me know. Okay. Yes, question number 10. Which electron source minimize the chromatic aberration best? What is the chromatic aberration? Let's ask ourselves, what is chromatic aberration? Chromatic means color. Color means different wavelength. So what is happening? The one, due to the spread in the wavelength are different. The electrons which we are getting, it's of the different wavelength. It means that there is the spread in the wavelength will create the spread in the energy, right? So the energy which is like, if from the electron source, this gun, if we are getting the wavelength of the wide range of wavelength, in that way what will happen, that the spread will be there. The spread in the energy will be there. And that spread in energy will lead to the lower resolution. It will create the aberrations, because we know different energy, different wavelength, they will converge at different points, right? Just like we saw in the lenses when we are discussing about the optical lens. In that case, we saw that different wavelength will converge at different which can more or less lead to the, instead of a point, it will lead to the something like a disc. So it's more or less decreasing our probe size. It's creating that error onto that. So how we can minimize it? By minimizing the spread in the wavelength which we are getting. So the tungsten thermionic gun, this one, the spread will be more in this. Then there is something known as lab 6. Here we will have a sharp tip, and due to which and also the work function we are modifying it, it will have a better the spread in the wavelength will be less. In the field emission gun are the best. These are the one which like all the SEM, majority, all the good SEM that are there, high energy SEM, with which you are going to the nano scale. Okay. It's using the field emission gun. This is the one, field emission gun, also known as FEG, is the one which is having the best resolution. You can remove this chromatic aberration to a very large extent in this particular FEG. So the right answer for this will be the option C. Also, remember, the same thing will be true for the brightness also. Okay. So this was the question number 8. Let's move to the question number, again, see, we talk about the chromatic aberration. Now let's talk about the spherical aberration. Chromatic aberration you can remove to a very large extent. But spherical aberration, you cannot do anything for that. Spherical aberrations are like, you can just reduce it to certain extent, but after that you cannot. Why it is happening like that? It is happening because the electron which is passing near to the optical center, they will converge at different point compared to the one which is passing far away from the center. More or less, again, if you see, like, okay, it's again creating the disk of this confusion, like the disk is there, instead of a point we are getting the spread. How you can minimize it? Let's not allow this particular, let's put an aperture, and let's not let this particular beam to pass. So by decreasing the aperture, by decreasing the electron intensity, number of electron going through it, so we are not letting the electron which is far from the axis to go, we are only letting the electrons which are near to the axis to pass through it. In that way you can minimize this thing, right? You can minimize this particular spread, but you cannot completely remove it. One more thing we are doing is that since you are cutting out the electrons, the beam intensity, the brightness, you are decreasing it, right? So the number of electron which is striking the specimen, you are decreasing. So that is also is there to, the role is playing. Okay, so there is always a compromise here. Something you will try to win, something you will lose. So now let's talk about the spherical aberration in an electron lens cause image rotation, color fringes, point object to appear as a disk. So instead of point, it will be like, let's say we not remove the spherical aberration, we let it like this. This path is telling that, okay, now focus on the same point. It gave, okay, the image is this. This one is giving, no, image is this. So on an average, what we will get for a point, we will get a big disk. Is it true for the electromagnetic lenses? Electromagnetic, yes, it is true for the electromagnetic lens. I'm just taking the analogy from the optical. They are exact, they are same. It is true for the electromagnetic lenses. Yeah, so instead of a point, it will appear to be a disk. So the point object will appear as a disk. So this aberration is needed to be removed. Okay. Yeah. So yeah, this was the answer. Option C is the right answer. Okay. With that, we have solved the question number 11. Let's go ahead and solve the question number 12. You will find the same or similar question in the class. Okay. In the class assignment, week 3 assignment. See, advice from my side, who are giving the exams of this particular course, you should know about how things are varying, how this, on what factor, on what things it is depending upon. We have to find the optimum resolution, aperture semi-angle. Due to audio issue, please repeat again spherical aberration. Spherical aberrations. Yeah. So yeah, what we discussed till now, that we cannot remove the spherical aberration completely. Let's talk about it. What is causing the spherical aberration? Spherical aberration, what is this? That the beam, the electron which is far from the optical axis, this is optical axis, let's say, the far from the optical axis, they will converge at a different point than the one which are near to the optical axis. They will converge at the different point. So these points of convergence will be different, will differ. Due to which, instead of a single point, single source of point, what you will get a spread. This is what the spherical aberration is. So what you are doing, like, the beam size itself is increasing. Beam size increase, we know that the resolution will be decreased. So if we are not removing the spherical aberration, our resolution will be very poor. Now again, how to remove it? How to remove, it's a wrong word, how to minimize it, how to decrease this particular effect, this aberration. Let's say we are putting the aperture over here of this particular one, and we are not letting the electron which is far from the axis to pass. We are only letting the electron which is near to the axis to the pass. In that case, what will happen? The size of this particular, the disk of least confusion will decrease, will keep on decreasing as you keep on decreasing the aperture. But you know, like if you keep on decreasing the aperture size, what will happen that the number of electron which is passing through the entire optic path will decrease. Less electron, less brightness, less is the interaction with the specimen. Our aim is to interact the electron with the specimen. So when you are trying to decrease this aperture, but to minimize the spherical aberration, you are also decreasing the number of electrons striking, the current which is striking the specimen. Okay. So this is on an average entirely the spherical aberration which we need to aware about. Now, let's move ahead. How to minimize this? Like, see, we talk about that, how to minimize these things. Now we can put it in the equation. See, this optimum, beta optimum, it's the angle at which we are collecting the informations. Okay, so this is the semi angle, this is the axis, this is the where we are collecting the information, let's say, till what. So if I'm keep on decreasing the beta, what is happening? Spherical aberration is decreasing, but also the intensity of the electrons, the intensity of the beam is decreasing. So we have to find some optimum value. So this is the equation which will tell you the optimum aperture semi-angle. And this is the one which will give you the resolution. Right? So what we have to do? We have to put the wavelength, and we have to put this is the coefficient of spherical aberration. Okay. So these two things will be given to you in the question. So we can see that the wavelength is given to us, and this is given to us. One thing to note down, they both have the same unit, right? Like the same dimension, they will be in the, then only it will cut the lambda and CS. See, so the equation is 0.67 multiplied by lambda divided by CS to the power of 1/4. One thing I would like to tell you, this value 0.67 which is there, different book will give you the different value. Okay. So our concern should be on these parameters. And for the exam, I will tell you that, okay, better you remember these things, because the questions can be as it is replicated in the exam. It's very simple. Beta you can find, lambda, CS you can substitute, lambda and CS you can substitute here. You will find the resolution, optimum resolution. I think we don't need to do this mathematically. We know that it's very easy. We can just put the values. If any doubt, let me know. If not, let's move to the next question, question number 13. Okay, yeah, let's discuss few concepts before we move ahead. So here, just a second, guys. So this is our electron probe. It's coming. It will have some diameter. We might think that this is a resolution. The probe size is a resolution. No. Inside can happen that even though you are focusing on this region, it will extract the information from this much region. So different signals we are getting. Again, we are going to discuss about each signal in much more detail in the upcoming week. Let's have a look on to what are the signals that we are producing. Secondary electron, which we talked about. Backscattered electron, which will be deflected back by the nucleus. The characteristic X-ray will also produce. And below this also we can generate that white radiation in the X-ray, continuous X-ray. Okay, those things will be there. From the figure, you can understand that to what level, what is the level interaction volume is it, how much interaction volume is there. So on and this is how the interaction will look like. The electron is going, it's interacting with the specimen. Now the signals are generated through it. It's not as smooth as this. It is more or less like this. It's very random. But you can more or less you can see that okay, the shape is like a tear shape. So now, yeah, I want to discuss few things here. Let's talk about the transmission electron microscopy. The thing which is discussed in the class, I will try to cover that part. So now, see, if you treat electron as a particle, you can also treat it as a wave. When we are treating it as a particle, we'll talk about the phenomena like the scattering. Right, scattering, it can be elastic, it can be inelastic. The energy can lose, energy can be as it is. When we talk about the wave, we'll talk about the interference. Let me tell you, in this particular week, we not discuss about the wave interference, wave nature of the electron. We'll do in the upcoming weeks. Let's now discuss in detail about the particle scattering. What is happening? So the particle can scatter this electron. It can scatter from the electron which is present inside the specimen. It can scatter by the nucleus. Right? So this is my specimen, let's say. The electron is coming. We are talking, let's say, in the transmission geometry right now. It will go. The direct beam will also be there. It will pass through the specimen. Few beam will also be scattered here and there. Now the scattering, we know that, let's say electrons are scattering by the nucleus. Let's talk about the forces. Two charges, they will have some force. They will have force. Now, more is the charge, more is the force, more is the scattering. Like more it will deviate, right? So we talk about the nucleus. Nucleus is there, it will deviate from the path. Like it will make our electron, the one which is coming. Our incoming electron is having the same charge. It's an electron is having 1.6 into 10 to the minus of 9. The charge is fixed. The nucleus, more is the charge on the nucleus, stronger the nucleus is, more is the scattering, right? More it will deviate. So let's say this is the nucleus in case 1. This is the nucleus in the case 2. This can happen because when we are increasing the atomic number you increase, the charge on the nucleus will increase. So this one, same electron is coming to both of them, it can deflect a certain way. The deflection will be more here because the charge is more, right? The scattering will be more. I hope I'm clear here. So the interaction volume we can, now we talk about the Z. So how the Z is changing. So if I'm increasing the Z, what is happening to the scattering? Let's say sigma is representing the scattering. What is happening to this? This is also increasing, right? Z is increasing, sigma is increasing. The more is the scattering. Now let's talk about the angle. Okay, I should take one more paper, one more paper. Okay. Okay, I applied the electron is coming. Now it is direct beam is there. Now the scattered beams are also there. Let's say right now the theta is 0. Here the theta is 0. Here the scattering is there. If I'm increasing, keep on increasing the theta, the number of scattering, the scattering point which I'm getting is low, right? If I'm increasing the theta is increasing, the overall the scattering, the intensity of the scattering will decrease. Here there will be more scattering nearby, the far will be less scattering, right? It's more easy to deviate by little extent instead of the large extent. This is general for the all the specimen. If you're moving away from the axis, you will get the less number of scatterings. Now let's talk this particular things, like like in the class there is a lot of equations which we put. Those equations I try to generate like what they mean. So now first thing is that the theta, the scattering angle. If I'm keep on increasing the scattering angle, I'm finding that the intensity of the scattering is decreasing. The first one we have understood. Lambda is not the wavelength. Lambda is a mean free path. What is the mean free path? Mean free path is a distance traveled between the two scattering event. Okay. The first scattering happened, no, second scattering. The distance traveled between that will be the mean free path. So now, if the scattering is more, if more is the scattering center, the mean free path will be less, right? If the distance between the consecutive scattering will be, the distance between the consecutive scattering will be more, the lambda will be more. If the scattering is more, okay. No, this is not. If I'm decreasing the wavelength, if I'm decreasing the voltage, let's talk about the mean free path later on. If I'm decreasing the voltage, what is happening? The scattering will, now let's say I'm having this specimen, I applied the energy, case 1, case 2, again I applied the energy, 1 and 2. E2, the energy is more than the E1. So what will happen? Which one will scatter more? You can think of it like you have a ball. Let's say the cricket match is going on. You throw a ball with a very high speed. Deflecting that will be difficult. This will scatter less. The energy to divert the ball which is with the high energy, to divert the particle which is moving with the high energy will be less. While the one with the lower energy will be the more. So lower one will scatter more compared to the higher one. Okay, so this is clear. The second part is clear. The third part also we have discussed. If we are increasing the Z, what is happening there? The sigma is also increasing. More is the Z, more is the atomic number, more is the charge on the nucleus, more is the scattering, more scattering will occur. Based on that, let's try to answer a few questions. I made these questions quite late. That's why I'm not able to print them. So let's try to answer it. I'll read it. My handwriting is not as good. Among A and B, which curve correspond to the 100 keV and 200 keV electron beam? Let's talk about the particular theta, particular angle. So we fix the angle. So what is happening? B is showing the less sigma. The sigma of B is less than the sigma of A. So which beam will be having the more energy? Corresponding this will correspond to what energy they will be, like E of B and E of A. Which one, whether it will be more or it will be less? So A is correct or B is correct? We know Higher is the energy of the incoming electrons, less is the scattering. Higher is the energy of the incoming electron, less is the scattering. Right, see the voltage is decreasing, so the scattering will increase. So what we can say from here, what do you think? A is right answer or B is right answer? B1 is showing the less scattering compared to the A1. So now the discussion which we made till now, from that what we can say, since the B is showing the more scattering, the scattering in the B is more compared to the A, it means that the energy, the electron beam energy of the B is less than the electron beam energy of the A. Okay, so this is the right. The option B is the right. Oh, sorry. I made a mistake. B scattering less, right? B scattering less means the energy of the B will be more. So option A is right. Pardon. The one which is scattering more, the more is the scattering, less will be the energy of the incoming electron. Okay. More is the energy, difficult to scatter. So option A, since it is scattering more, the energy of A will correspond to the 100 keV. The B one, it will correspond to the 200 keV. Am I clear here? If yes, let me know. If not, then we can have a discussion on this. Okay, great. Since there is no doubt, let's move ahead to the next question. Question number. Okay, there is no question number. Let's try to answer this. Now again, among the following options, which one is the correct? Figure below. See, we got some scattering at particular different angles for different materials. Z1, Z2, Z3, it's their atomic number. We want to comment on this, like Z1 is more or Z2 is more or Z3, like what is the order? In which order it will be? So what do you think? Let's talk about the particular theta. We fix the theta. We are not going to change the theta. We are not going to worry about that. So what is happening over here? We know if the atomic number is increasing, that is the charge on the nucleus. The charge on the nucleus will increase. It will increase the deflect more. Deflection will be more. It will scatter more. The scattering will increase. Scattering will increase. This will increase. They are in hand to hand. More is scattering in the Z1, like the sigma 1, sigma 2, sigma 3. If I am talking about the scattering, sigma 1 is more, we know from the figure. Sigma 2 is more, we know from the figure. From here, from this particular thing, we got to know that Z is increasing. It means that the charge of the nucleus is increasing. It means that it will deflect more. Okay, it will scatter more. They are going in hand to hand. So we can say that the Z1 will be greater than Z2 will be greater than Z3. So the right answer is option B. Okay. Let me know if there is any doubt in this question. Okay, since there is no, let's move ahead to the next question, question number 13. The probability of electron scattering, the probability of elastic scattering at a fixed electron energy E naught decrease with increasing what? The probability of elastic scattering, let's forget about the term elastic scattering, let's concern about the scattering. You will find this question similar question in the assignment. The probability of scattering at a fixed electron energy E naught. So we fix the beam energy. So they are telling that under what condition sigma will decrease. atomic number. So we are getting the few answer to be the atomic number. We want to decrease this with increasing. Something is increasing. Okay, let's since you guys told the option A, let's talk about the option A. Let's say Z is increasing. Atomic number is increasing. It means that the overall charge on the nucleus is increasing. It will deflect more, like more bending will be there. If bending is more, it means that it will scatter more. That means that the sigma will increase. So increasing the Z will not increase the sigma. So option A is incorrect. What about the scattering angle? Let's talk about the scattering angle. We transfer the beam. Now scattering at the different angles. What we have learned in our initial discussion, that more is the angle, we will find that the less number of scattering points will be there, scattering will happen. So if you are deviating, like let's say this is a direct beam. If you go very far away from this, if the theta is very large, you will find that there is no scattering. The scattering is zero, very far. Come closer, theta, keep on decreasing the theta from this to this to this. The scattering will increase more and more. So what we got, that if I am increasing the theta, if I am going away from the optical axis, direct beam, if I am going away from the direct beam, the sigma is decreasing. Okay. So we'll find this question. You will find this question similar. You will be able to get the same question in the assignment, more or less. So the right answer is option B. These two are just I put something. Nothing to worry about. Scattering angle is the one. Right? Let me know if it is clear. Seems like there is some confusion. You guys are not responding. If there is, please let me know. Okay, let's move ahead. We might be able to cover up in the upcoming discussion part. Increasing charge of the nuclei influence the elastic interaction with an incoming electron by increasing the charge of the nucleus. You are increasing the charge of the nucleus. That is, you are increasing the Z. Okay. So what do you think? Among this, which one is the right answer? Okay, so the answer is A. Decreasing the scattering angle. Increasing the charge of the nuclei, influence the elastic scattering with it. Z is increasing. Q is increasing. Deflection will be more. Deflection will be more. Deflection will be more. It means that the bending will be more. So overall scattering is more. So if I am increasing the Z, increasing the charge on the nucleus, it means that increasing the atomic number, influence the elastic scattering interaction with an incoming electron by decreasing the scattering angle, increasing the scattering angle. So the right answer is that if I am increasing the Z, the scattering angle will decrease. That's right. Okay. No. If Z is more, it will scatter more. It will scatter more, right? And the scattering angle will not decrease, it will increase. So the right answer will be option B. Decreasing the intensity of the scattered beam, there is no correlation between them. C and D are incorrect. See, we know Z is increasing, the charge is increasing, deflection will be more, bending will be more. Bending will be more mean that the theta will be more. Theta will not decrease, theta will increase. This is entirely we are doing till now. We are saying, okay, the charge is more, it will deflect more, theta will be more. Instead of deflecting by this much amount, it will deflect by large amount. The scattering angle will increase. Right? So the right answer is option B, not the option A. Somewhere am I not able to explain it properly? Seems like see, it's easy, it's simple. All we need to understand that the charge is more. Electron will experience more force. We know, right, that electron will revolve around the nucleus. If this force is more, it will rotate more, it will deflect more. If the force is less, it will deflect less. Okay, let's see the question. It's good that we should ask the question. If the scattering increases with increasing in atomic number, then brightness of the higher atomic number in the SEM should be low. However, the other way around. Okay, let me read it. If the scattering is increasing with increase in the atomic number, then the brightness of the higher atomic number in SEM, should be low. However, the brightness of the higher atomic number should be low. No, it's see, you are thinking it. Let's see. I got your question that you are asking it from the backscattered electron perspective. Let's first of all, this entire thing which we have discussed is for the TM. Now let's talk about, for your concern also, we'll talk about the same thing. In the BSc, the one which we are getting in the detector, the electron which we are getting in the detector is nothing but a primary electron itself. Let's not write those things. See, BSc is a primary electron. What we are getting is the primary electron. So now, let's say Z is more. Let's say I'm representing them by the larger, small. So what will happen? It will go. It will deflect back. Z is more. It will deflect back. Z is like it will not be able to deflect. It will be able to deflect to certain angle. Now you got this from the specimen. They said this is my specimen. This is my specimen. In the BSc mode, now you think detector is somewhere over here. Okay, so detector is over here in the ring form. Will it be able to capture this electron, or it will be able to capture this electron? Case 1, it will get easily, or case 2, it will get easily. In the case 1, right? Because it is deflected more. More is a deflection. BSc signal is more. Okay, I hope it's, yeah, is it? BSc signal is more here. Just a second, guys. There is some connection is lost. Pardon, there was some network issue on my end. So now, so I hope I'm audible now. Yeah. So, am I audible now? Can someone let me know? Yeah, great. There is some fluctuation in the internet. Yeah. So in the case 1, we will get BSc signal easily. So higher Z atom, that's why appear brighter, because they will give more BSc signal compared to the lower Z atom. They will not be able to deflect to a very large extent. Very few electron will be the only one which will be able to deflect. So this is the reason why we are getting the more signal, more brightness in the, why we place the detector above. Uh, See, yeah, these things are there. Why we are placing the signal? See, BSC detector we are placing just above. The reason is simple. That because the trajectory is like that. It is deflecting back, more or less, right? It's deflecting back. So we cannot keep it at a certain angle. If we keep it at a certain angle, this will not be captured. The detector will only be able to detect it if they both are like, if the electron goes to the detector and the primary electron is more or less like 360-degree rotation, we can say that their path is, instead of this, it changes to like this. It's not changing to this. For SCM, we can place it at certain angle. For BSc, we are placing it like this. Again, I will tell you that these things we are going to discuss in detail in the upcoming lecture, because the SCM is not started yet. We just now only discussed about the TM and SCM in the general way. We'll discuss these things. So I hope I'm clear to you. So let's again revisit this. Again, let's revisit this. Z is increasing. It means that the Q is increasing. The charge is increasing. The charge is increasing, it will deflect more. Now we are talking in the TM geometry, okay. Here it is deflecting less, here it is deflecting more. Deflecting more. Z is more from here to here. Charge is more, it will deflect more. Bending will be more. See, we see the bending is more. So bending is more mean that the theta, the scattering angle will increase. So this is how it is. If I'm clear, let me know. If not, we'll discuss it again. Okay, let's discuss few, if there is no doubt, let's discuss the few questions. Now, we are going to discuss few easy questions. Before that, since we are discussing this part itself, so let's discuss this last question. There is figure A and the figure B. This is A and this is B. Which one correspond to the low Z atom? See, we pass the this is our specimen, incoming electron B. In both the cases, everything is same. The thing is that their atomic number we don't know. Z1, Z2. Okay, or you can say ZA, ZB. So among them, which one is having the low Z atomic number? Ahmad, very good. The option A is the right answer. Low Z. Since Z is low, it means that Z is decreasing, mean that the charge on the nucleus is decreasing. Bending will be less. Bending is less, mean that the theta will decrease. So here we can see. So this is low compared to this. It is of the, let me tell you now, this is copper and this is gold. Gold, we know that it will have the higher atomic number. Since it is having the higher atomic number, the scattering angle will be large. Here, the scattering angle will be smaller. We cannot say that there won't be any scattering at the higher angle. There will be that, but it won't be as significant as it is over here. This question is done. Okay. Now, this question is done. Now I'm just telling few more things that, okay. Now you see from the angle, right now, 0 angle. Keep on increasing the angle. What is you are seeing? The theta is increasing. If the theta is increasing, if I keep on increasing the theta, our scattering is decreasing. The instance here there is a less scattering. Here there is more scattering. Here there is more scattering. If we are getting near to the, this is theta. If theta is decreasing, we are able to see the more and more scattering. Okay. So this is also we can. So let me tell you this pictures I have copied from the Barry Carter. Okay. Let's move ahead to the next question number 15. Now it's easy. Which of the following is a characteristic of the elastic scattering? Elastic scattering. What do you think? Elastic scattering. Elastic scattering, what it means? Option A, energy loss occur. Only the direction of the electron change. Secondary electron are emitted. X-ray are generated. Elastic scattering. Scattering is happening. It means that the direction is changing. Direction will change. Elastic scattering. Elastic means that there is no loss in energy. Elastic means that the no loss in energy. Right? If there is a scattering is elastic, there is no loss in energy. But scattering is happening, so the direction will change. So what is happening? Only the direction of the electron is changing, not the energy. So energy is remaining same. Energy loss will occur? No. There are certain cases which we can talk maybe later on. The energy loss will occur, but very small. Very small. It won't be very large. And that small energy loss will be the Prahlad is saying right also that okay, there will be energy loss also. In certain way, this is also correct. But on the larger picture, if we talk, even though the path is deviating, see, we know whenever the charged particle is deviating its path, it is losing some energy, which is what we call that the continuous X-ray which is generated. Right. So, but that much energy, that's much small energy, we will not consider that to be the to call it to be the inelastic. The scattering is still elastic. So energy loss is very less. The direction is changing. So if it is MCQ, only one answer is correct. I will write this. Okay. Remaining things are not correct. Okay. Any doubt? Let me know. Incoming electron strike electron and loss of energy will be. That is something which we known as the inelastic scattering. So what is happening that if the incoming electron, primary electron, if the primary electron is there, if it is interacting with the nucleus, it will generate the elastic scattering. There won't be change in the energy. While if it is interacting with the electron, then it will be considered as the inelastic scattering. The scattering is of two types. So the Prahlad is saying that incoming electrons strike electrons and loss of energy will be there. That is there. So that is known as the inelastic scattering. Right now, our concern is about the elastic scattering. So in elastic scattering, there won't be loss of energy. Okay, great. Let's move ahead. Let's go to the next question. Question number 16. First one. Inelastic scattering result in the energy transfer from the electron to the specimen. Is it true or false? In elastic scattering, if the scattering is inelastic, will there be energy transfer from the electron to the specimen? Yes, it will be. Inelastic means that we are losing some energy. Where that energy is going, it's going to the specimen itself. So the answer is true. We'll find about this particular question, the question number, this first option. We will have a detailed information in upcoming weeks. Very detailed. Second one, the thermionic gun produces high coherent electron beam. Thermionic. Will it produce the coherent electron beam? The answer is no. It is the PEG, field emission gun. So here it's a false. The coherent beam, we know that coherent, it should be like more or less same wavelength, same phase, same energy. Right? Last, the third one. Elastic scattering is crucial for the diffraction experiment in the TM. Yes, it is. When we discuss about the TM now, we'll see that this is the diffraction which is happening, the elastic scattering, which is crucial for the diffraction. See, what we just told that it will deviate a lot, deviate from its path. This is the one which is going to correspond to that diffraction experiment, diffraction things. So we are going to discuss in detail the reciprocal, that is how the diffraction pattern is being formed. Those things will be there. Okay. So option C is true. D. Backscattered electrons are generated due to the high angle elastic scattering. Backscattered electrons are generated, BSC electrons are generated due to the high angle elastic scattering. What do you think? Is it true or is it false? Backscattered electrons. Here, the scattering is less. While if we talk about the backscattered electron, the scattering will be more. So, backscattered electrons are generated due to the high energy elastic scattering. Why elastic? Because it is interacting with the nucleus. It's not losing its energy. It's not colliding with the electron and losing the energy. It's interacting with the nucleus. So, it's elastic scattering, true. Backscattered electron generated due to the high angle elastic scattering, this is also true. Right. So, option D is again true. Interaction cross-section decrease with increasing the atomic number. Interaction cross-section, like more is more interaction, more scattering. More interaction cross-section means that the more the scattering, more scattering. Scattering will be more. Like sorry, the scattering, the interaction cross-section, that is known as scattering. We can take some analogy. Okay, it is more or less you can interact, you can relate with the scattering. Scattering will decrease with increasing the atomic number. What do you think? They are telling that scattering will decrease with increasing the atomic number. Is it true or false? Atomic number, that is Z. If Z is increasing, the charge will increase. Charge will increase, band will be more. It will increase more, it will more scattered. We just now saw in question that here Z is more, copper is more, higher atomic number. Here the interaction is more than compared to the low Z, right? So the answer here is false. More is the atomic number, more will be the scattering, more will be the interaction, more will be the interaction cross sections. Okay, so answer is false. In this entire part, if any doubt, please let me know. Okay, let's cover few questions. I think the time limit is there. We'll try to cover 3 questions more. 1. Elastic scattering. Probability of scattering event, no energy loss, only direction change, energy loss occur, fact, high angle scattering. So first one is going to match with which? Very good, Ahmed. It's elastic scattering, no energy loss, only direction will change. That is option A is the right answer. Option B is the right answer. Inelastic scattering. Second one. Yeah. Very good. Sangeet Kumar, right? It's the option B, right? Elastic scattering is a B. Now, inelastic scattering, yeah, energy loss will occur. That is option C is the right answer. Coherent beam. With what we can produce the coherent beam? Coherent beam, we know that coherent beam will be the option D. With the fixed source, yes, very good. Option D is the right answer. We can produce the coherent beam. Backscattered electron. What is the backscattered electron? Backscattered electron are nothing but the, which one will be the right answer? The answer will be the E, right? High energy scattering, high angle scattering. So high angle scattering are the backscattered electron. This is the option. Interaction cross section is nothing but the probability of the scattering event. Remember this. Interaction cross section is the probability of the scattering event. More the more is the scattering, it means that the more is the interaction cross section. So fifth one is the option A is the right answer for this. I hope it's clear. Let me know if there is any doubt in this. Yeah. Auger electron, secondary electron. Again, I will tell you. Auger electron and scattering electron. About this, we are going to discuss in large extent that under what case auger electron is used, in under what condition more auger electron will be there, what is the effect of the Z on the auger. Right now, let's talk in the very general way what is happening. Auger and the secondary electron are primarily generated from depth of the interaction volume, bottom of the interaction volume, away from the interaction volume, surface of the specimen. Auger electron is the one which is having the low energy, very low energy, while the secondary electron is having, again it's having the low energy, but compared to the auger it's having little high. So still we will call it to be the low energy. Typically will be less than 50 electron volt. 50 electron volt. On an average, it will be less than 50 electron. Since their energies are less, they will only be, will get it near to the surface. We won't get from the depth. From the depth, we will get BSc. We will get characteristic X-ray. Okay, those things we will get. So the auger and secondary electron are primarily generated from the surface of the specimen, near to the surface of the specimen. It's not the depth. It's not from the bottom. Like it's not from the bottom. It's not from the away. Okay, it will be near to the surface. Okay, so question number 18 is done. An electron beam, when focused on the surface of a specimen, can penetrate through it if the specimen is thin, can scatter through if the sample is thick. Penetrate through if the sample is thin. Let's talk about the two things. Electron beam is coming, the specimen is thick and specimen is thin. If the specimen is thick, it will be concise, like it will just scatter through. It will not penetrate. In the thin, it will be penetrate. In the thick one, it will be scatter. Okay, so which one is the right answer? Can scatter if the thick, penetrate if the sample is thin. So option B is the right answer. Can penetrate regardless of the specimen size, incorrect. Can penetrate if the sample is thick. Can scatter if the sample is thick. D is right. Can penetrate if the specimen is thin. A is also right. So A and D are more or less like a subset of B. So if it is only one MCQ type, I will go with the option B to be the right answer. MSQ, I will take the remaining all three. Okay, let's solve this last question. With this, we will wind up. Between the backscatter electron and secondary electron image, BSc image usually has the low spatial resolution than the SC. Both have the same spatial resolution. What is the spatial resolution? We know that secondary electron is generated from here and backscatter electron is generated from here, like till this much volume. We think that our beam size is this, so this is the resolution. SE is more or less close to that. BSc, the spatial resolution is very poor. Instead of this, it is giving the information from this much distance, from this much width. We are thinking that the spatial resolution is this, but the BSc, we are getting the signal from this much. So the spatial resolution of the BSc is poor compared to the SC. Okay. So BSc image usually have a low spatial resolution than the SC image. This is true. Okay guys, so this was all from my side. If any doubt, whatever we have discussed till now, then let me know. If not, then we will wind up this particular class. Not only in the things that we have discussed, even in the last week's or thing that is discussed in this week class, you can also let me know that. Okay. Please solve question number 18. Yeah, here. Here. Yeah. Yes, yes, Ahmed, it will, the entire video will be uploaded. Okay, I will show you just now how it will be. Yes, Pradal, let me know if there is any doubt in this question number 18. You can also unmute yourself and interact with me whenever, if you feel to do so. All are okay? Okay, great. Okay, so let me unshare my screen. So where it will be uploaded, let's see where it will be.
Regarding question 18, what I think every year you have given the tick marks, correct? Now, for example, when there will be exam will be there, it will be MCQ will be there, then it will be confusing to us which one to tick.
Among the 18, in this 18th,
Every another option should be there, A, B, above all, something like that. Because every year it is a 18, everything is the, it seems the okay answer.
for this particular one, it is the answer, option D is only the right answer.
One two cases you have told that this will be correct, this is better answer, this is the less right answer. One more question was there,
Question
not
number
this
19.
one.
Yeah, I got it. This one.
Somewhere it is there. Yes, sorry, this one.
Yeah.
Now, for example, B is the more better answer than A and D, correct?
Yeah.
My only small query that when exam will be there, it will be MCQ based, correct? Online.
Yeah, it will be MCQ.
Not
Yep. Mhm.
online or offline.
It will be online. It will be computer based exam.
Now in that scenario, answer what will be given? Somewhat given A or D, they will be get 0 marks, correct?
Yep.
But perfection, this is the thing. Is you take care, please take care while forming the question. That is my input.
Uh, Even whenever we solve any question, in that it will be like the confusion will be created. It will be created, and it's up.
It is strategically will be created. Okay,
It
that's
will be
fine.
it will be on us to select the best among them. So nothing can be wrong. So there is a lot of concept that we have discussed in the class. You cannot say something is like, we are not black and white. We are always in the gray region. So among that, which one is more better? That is something which we are going to select. In this thing, in this question, it is like, okay, the B is the one which is like the larger extent. It is more correct compared to the A and D. That's why we selected it. So it's up to us how to decide which one we should put. Even while solving the assignment, you will face some difficulty, something like this. Maybe in the week 2 you might have faced few difficulty while solving the questions. So this is the one. We will try to minimize all these things, like there should be one answer, but again, it's a task for us also, that okay, we have to understand what we are going to put. Okay.
Okay, please just keep in mind. That's all I'll say last. What you are told, we'll minimize it. I guess that is the only point I would like to say. Thank you.
Yeah, so let's solve that Ahmed's problem, that okay, where it will be saved. Let me share my entire screen. So you can go to this particular entire this website, where from where you are accessing the week content. So here you can go to the problem solving session, and you can click on this. Here you will get a link that will direct you to this particular Excel sheet, where we, like, there is a two scholars. One is me and one is Jagruti. So we both are putting ours. So after 2 to 3 hours, I will put the week 3 lecture over here. Okay. So you can click on that and you can access it. Also, you can go to my website. You can access all the videos which we have already discussed. Okay. So that was all, I think.
Here, excuse me.
Yeah.
Mr. Mishra, I would like to know if there is any model question paper we can get it in the latter stages before examination. Model questions, something like a previous questions of the same NPTEL examination. That kind of things, is it possible?
You cannot get the entire question paper of the previous year, but one thing I will tell you, that the majority of the questions will be can be same as it is. So I also attended the few exams of the NPTEL. So from the courses I found that okay, they are like more or less 20 to 30% of the question is reflecting same which we are solving the assignment. So and the
Okay, got it. Thank you.
and the way the questions
Yeah.
are asked are also the same, the one which is asked in the assignments. So they will be of the same level. Right? Yeah.
Okay, that means the assignment question, there is a possibility to repeat, or it is kind of similar question, it will be repeated. I mean, it's identical or similar.
Yeah, but don't think that it will be exactly identical. The variations will be there. So maybe at the end you be careful that okay, you are able to handle the things. So the model question paper which you are telling, it's more or less like the assignments.
Okay, got it. Thank you.
Okay, guys, any more doubt? Since there is no, we can wind up today's class, and I hope to meet you all again in the next week, same time, same day. Okay, bye bye.